Hello students, welcome back. Previously we discussed the derivative formulas for exponential and logarithmic functions and did some exercise problems, but most of those, if not all of those, were reviews. So nothing to be concerned with. Basically these two rules which we had been using, as a matter of fact. In our textbook they didn't really deal with those too much, even though they could have, but in my lessons throughout week in, week out, we had been using exponential and logarithmic a lot for natural exponential and natural logarithms, of course. And as for arbitrary basis, well, we don't really use these anyway. I mean, you can always convert everything back to natural exponential and natural logarithm anyway, so why would anybody bother with these? We went through these problems. Straight ahead, product rule. Product rule combined with the chain rule, and the use of chain rule is always tricky. This one, quotient rule. And then when calculating the derivative of the numerator and the derivative of the denominator, chain rules there. Alright, how about the next problem here? Answer the questions regarding the given function, and we have a logistic growth model. Alright, find all asymptotes. Well, algebraic expression is here, and then the problem asked you about asymptote, or minimum or maximum, those kind of thing, increasing, decreasing. The very first thing you should do is to graph this function, and then take a reasonable guess before starting anything. So go ahead and open your favorite grapher, and then plot it. Okay, I'm using mathematical command, but you could have used your handheld calculator or other tools like Desmos graphing calculator. From negative 10 to 10, I cannot really see a lot, so let's go to negative 20 to positive 20. Okay, asymptotes are forming here and there. Negative 30 to positive 30. Clearly we have asymptote here, y equal to 0, and I expect y equal to 100. And indeed, 100 is right up there, the equilibrium. So find all asymptotes. To the left-hand side, I have to take the limit toward negative infinity. To the right-hand side, I have to take the limit toward positive infinity. And then we already know the answer. Y equal to 0 and y equal to 100. Okay, let's go ahead and do your computation. Here's a graph. And then take t to the positive infinity to the right-hand side limit. E to the negative infinity here because bigger font. E to the negative infinity here because t is going to positive infinity and positive times negative. So this is 0. So 2 times 0, so that whole thing is 0. So we have 100 over 1. 100, that's the limit to the right-hand side. So that's the horizontal asymptote to the positive infinity, to the right. How about to the left? It looks like I'm going to 0. Indeed, you're going to 0. T is going to negative infinity, so this is e to the positive infinity now, because negative, another negative. E to the positive infinity is infinity, times 2, that 2 is infinity, so basically we have 100 over infinity. That goes down to 0. So, graph will give you the answer, and then the justification are coming from the limit computations. Next, find the x-coordinates of all critical points and determine their nature. Well, let's go back to the graph again. Do you expect any critical point at all? Any local maximum or local minimum? Nothing like that, right? Here, this is just an asymptote, another asymptote, so this is not really hitting horizontal tangent. So I do not expect any critical point at all. Let's check. Take the derivative, set it equal to 0, and I expect no solution. Alright, take the derivative, and then instead of using the quotient rule, I decided to take this denominator as negative first power, this thing, and then apply the product rule instead. Why did I do it this way? I could have taken the quotient rule. In the end, I got this derivative. I don't know, somehow I don't like the solution I just did. Let's just do quotient rule computation. I have enough time, so let's go ahead and do that. So the derivative of this is, let's see. Oh, I see. This doesn't have to be a quotient rule. As a matter of fact, yeah, this is not even product rule. 100 is just a coefficient. And then this is just distinct to the negative first power. So 100, this coefficient, multiply by negative 1 and subtract 1 from the power. And by the chain rule, multiplying the derivative of the inside. Oh, that's how I got this. Well, that's good, but let's use quotient rule too. Let's see how that works. So denominator squared. And then the numerator, we have u prime v and then u v prime. Bigger font will be in order. We have this quotient and also even bigger font. By the way, what is p? Okay. And what is the derivative of this 100? It's constant, isn't it? So that's just 0. What's the derivative of denominator here? Well, constant 1, so that goes to 0. I need this exponential part. Exponential always stays the same. And I have to multiply the derivative of the inside. T over negative 4, so it's negative 1/4. That's the derivative. Okay, so this whole thing is just 0. And then this one, if you simplify, oh, that's what you get. You see, 100 divided by 2 over 4, and then minus become plus. And the denominator is square, so always positive. And then numerator is exponential, always positive. So p prime never hits 0, always positive. We have no critical point because the graph increases all the time. And look at the graph, increases all the way. Okay, all right, getting warmer and warmer. Determine the intervals of increase and decrease. Oh, come on, it increases all the time. So intervals of increase is negative infinity to positive infinity, and there is no interval of decrease. Yeah, increasing all the way, and derivative stays positive all the way. We already checked that. Determine the intervals of concavity. Oh, okay, look at this picture. Looks like the concavity changes around here. Do you see? Concave up and hit this and concave down. So right here, I expect an inflection point. A point where the second derivative hits 0. And this is a place the first derivative is the biggest. So the population grows the fastest according to this logistic model. Or if this is an epidemic model, the number of patients grows the fastest at the inflection point. All right? So second derivative is equal to 0, and the second derivative computation is, in general, a huge pain in the rear end because we have some really tedious and dirty computation to do. So I'll just scroll and then show you the computation. And okay, all right. Here's the original function in terms of power form, and here's a derivative computation, all right? 50 exponential times this thing to the negative second power. Now, for the second derivative, we now have a product rule. Exponential times this power thingy. So this times that. So we use the product rule like this and set it equal to 0. And solving this equation, oh my goodness, how do you solve this equation equal to 0? Don't be too intimidated. A lot of things just cancel each other out, like 50 and 50 cancel each other out. Exponential cancel each other out, and so on and so forth. And then, oh yeah, this 1 plus 2, this is negative second power. Negative second power. That 2 cancel each other out too. And then what's left here is going to be just this one. And then we have exponential is 1/4, so taking a logarithm and doing, you get 4 log of 4, which is 5.54. 5.54 around here, yeah, that looks like it. As for doing this computation with paper and pencil computation, oh geez, I don't know. I don't know whether this is appropriate for this course. In the exam, certainly I cannot write this kind of problem. It's tedious and takes too much time. But as a homework or as a project, I certainly can do that. So for conclusion, negative infinity to 4 log 4 around here, concave up, and concave down 4 log of 4 to infinity. And 4 log of 4 is about 5.545 around here, about here. Okay, we went through a logistic growth model with some calculus. Good for a project. I don't know whether this is good for exam problem though. I can make it work by giving you very simple numbers, only integers and so on. But if I do that, I will lose all the realistic nature. If I give you a bunch of realistic numbers, in that case, it becomes a numerical computation problem. I don't know. I'll figure something out, including discarding this topic altogether. How about this one? I'll just show you a picture. You end up with some exponential times something, some power function. Power function becomes 0 on x equal to 0. We get something like this. But exponential get pretty close to 0 when x is really large, so going down like this. And this expression is actually quite important in statistics. But I don't know whether this is going to be appropriate in 1325. So as for this one, let's skip it. Yeah, there's a good reason I de-emphasize it in gray. Okay, logistic model, that was it, I guess.